Yeah, so let's get started. This talk will be about Featran. It's a library for feature engineering in machine learning and data science. So let's get started. Let me introduce myself first. Who am I? My name is Neville. I work for Spotify in the New York office. I've been there since the office started in 2011, so it's about 6 years. Before that, I did search ranking, ML stuff at Yahoo. So at Spotify, I mostly work on music. Yeah, all right. So at Spotify, I mostly work on music recommendation, data, and machine learning infrastructure. So for the last couple of years, I worked mostly on machine learning infrastructure. And we use a lot of tools, mostly Scala for data pipelines and machine learning. So Shio, for example, it's one of our Scala API for Apache Beam and Google Cloud Data Flow. We also use Scouting in the past, Spark, and a couple of other tools. And we're also a big user of Parquet as well. So Spotify, hopefully some of you have heard about us. So we are a music streaming company. We have a fair amount of users and a lot of data collected from the users when they play music. And we use data to make recommendations, machine learning features, and all sorts of analysis. And data and ML at Spotify, it's a growing domain, and we're still collecting, and our data is growing as we speak, as our user base grows. And as of right now, we have probably 300 people writing Scala pipelines, and most of them are pretty new to the language and to the data science and data pipelining problem. We use Shio heavily for data pipelines, and in the last maybe year or so, people have written like 1,500 pipelines, unique jobs in production from scratch. So that's a lot of pipelines to maintain. And also machine learning is gaining a lot of traction within the company. We have 300 people either working on it or interested in machine learning. And then we mostly use Featran, Shio, and also TensorFlow for machine learning problems. So I'm gonna dive into Featran. So what is feature engineering? So machine learning, basically, it's a mapping of function, finding a function that maps your input data into some outcome. Your input could be labels, properties from user metadata, whatever, input source. And the outcome could be a prediction, whether the user will buy the service or not, or whether the user will click on an ad or not. So a lot of the time, it's clean up very noisy, unstructured input data into something the machine learning algorithm can, compute. For example, logistic regression or neural network, all sorts of different algorithms. They all treat, it's basically just function that's taking input numerical data and then generating outcomes. So it is, feature engineering is a big part of doing machine learning. And it's also very difficult and expensive. It's very tedious. A lot of the time, we're just writing pipelines, manually processing data. One example I often cite is when I used to work at Yahoo Search, working on the search query spelling algorithm. And that single GBDD tree has 6,000 features, and most of them are crafted manually. For example, the distance of 2 letters on your keyboard, that could be an important feature. And also, it varies by user locale. For example, English-speaking user will have a different, distribution of typos versus, say, a French-speaking, or even more difficult to predict, like a Chinese or Korean-speaking user. So these are very difficult problems to solve, and it's also a majority of the time where a machine learning engineer spends his or her time on. So, and of course, more quotes from famous people in machine learning about why feature engineering is important and how difficult it is. So we want to solve this problem. And we'll take a look at 3 basic feature transformers just to see how feature engineering works in general. So binarizer, minmax, scalar, and one-hot encoder. Binarizer is simple, right? Takes a numerical input, it could be a double, and then transform values into binary outcomes, either 1 or 0, based on the threshold. That's the rendering. All right. So in this case, the input is a bunch of numerical values. Let's say the threshold is 0.5. So the first 3 numbers gets binarized into 0. The next 3 binarized into 1. Simple enough, right? Simple mapping function. Min-max scalar, similar. You take a bunch of input numbers, normalize them to between certain scale. Often it's between 0 and 1, representing some kind of probabilistic distribution. So the same thing, a sequence of numbers input. We can normalize them to something between 0 and 1. And this is slightly more complex because we have to compute the mean and max in the original data set and then use that to normalize. One hot encoded, it's a slightly even more complex. We have input data that's some kind of string or categorical labels, for example, user's gender or a month or some kind of string input. And then we want to map each occurrence into a 1 in the vector and everything else into zeros. In this case, let's say an input is just a bunch of letters. This is what output might look like. A gets encoded into 1 and followed by a bunch of zeros representing other letters that's missing. Simple enough, right? Following so far. So now let's code it. How would we do that one at a time? So I have a Scala console. Just gonna define a sequence of numbers to start with. Let's say just some random numbers. Okay. Maybe we'll make it 8 numbers. Okay, 200. All right. Sequence of doubles, right? Simple enough. How do you do the binarization? It's simple, right? We can just do a map. Let's define threshold. I don't know, 42. So anything greater than 42, let's binarize it to 1. Make sense? Obviously, happens every time. Yep. Okay, so that's simple enough. Let's do the min max. So to do the min max, we have to compute min and max, right? Of course, this is a small data collection that's in memory, so I can just loop them over and over again. What if it's like a million numbers or billion numbers? I have to use some kind of big data processing, framework. So we'll probably do like reduce, right? So how does reduce work? Let's say I have a left-hand side and a right-hand side, right? So I can just do, turns out there's a function to do that, so let's just do that. This is reducing like, the mean using a single reduce step. I can do that with max as well, but that requires 2 reduce steps in the MapReduce framework. That usually means like 2 shuffle phases, which is inefficient, right? How do I do both min and max at the same time? I can just count running min and running max, right? So if I have one number, the number itself is both the min and max, right? Okay. So I have to do a map first, turns out. So I want to make it a tuple 2 and then reduce. See, it's pretty tedious. It's a lot of typing, and I've done it a lot. And this is only a tuple 2, so it's easy to keep track of. Actually, it's R. See, easy to make typos and mistakes. But anyway, let's do that. Dot max. So it's R arrow dot underscore 2, R dot underscore 2. All right. See, so now I can do both of them, in a single reduce step. This is still too much code. Let's try something else. It turns out Twitter, another company that uses Scala heavily, has built a library called Algebra, which they use heavily in Scouting, and also we use it in the other Scala frameworks that we use, like Shield and Spark. And it turns out that simple abstraction, the functional programming abstraction, can be applied to these kind of operations very easily. So I'm gonna just define an implicit class by adding a method to a sequence, so I can do all these algebraic reduction. So I'm gonna call it rich sequence, which is basically a sequence, but has an extra method. Okay. These are just language boilerplate. You don't have to define this yourself. If you use a library out of the box, usually they come with these kind of methods already built in. Implicit. What I want as a semigroup is a category theory structure or type, which basically defines any type that has a binary operation that's associative and commutative is a semigroup. So integers and plus, that's a semigroup. Integers, min and max, it's also they're also semigroups. Implicit, yeah, thank you. In this case, I'm just gonna do as reduce option. All right, compile the first time was let's see. So now we have the XS, right? And we can map it to tuple 2. Turns out algebra knows how to sum tuple 2 in parallel already, so we can just do that option. But the default behavior is just sum. It sums all the numbers. That's not what we want. So we have to wrap them in some kind of data type that defines the min and max operation. So we can do that. Min and max, right? So basically, I convert my input x into tuple 2 of two data structures. One is min and one is max. Both of them have some behavior defined, the sum behavior. For min, obviously, it's computing min, and max, it's the max. That gives me a tuple 2 of min and max, and then I can extract my numbers out. So tuple tilo underscore 1 underscore 2 dot get dot get dot get. So we can do x min, x max equals to these two numbers. Now we can do the min and max in parallel, which is great. So you can save a MapReduce shuffle stage. We have the min and max. It's easy to just renormalize the original data set with a map, right? So we take every original x, position it based on the min, and then normalize by the max, distance between max and min. That's pretty straightforward, right? Now we have a sequence of number that's normalized between 0 and 1. All right, so there's some recurring pattern we'll notice. So this, so far we've done it on a numerical sequence. Let's define a categorical sequence. So let's see, just some letters or strings in this case. Okay. Right. So I have a bunch of input strings. How do I compute the one-hot encoder for this input set? First, I have to compute the total or unique set of labels, right? Which is simple. We can just do toSet. That only works on Scala collection. We need to do that in parallel in MapReduce as well. So how do you do that? We can reuse the same pattern. Map. I map each individual string into a set of one string, and then do sum option. See a recurring pattern, map and then sum. What do I get in this case? It turns out a set of anything is and the union operation is also semigroup because it's associative and commutative. Now I have the set of the unique labels. I'm gonna convert them to a sequence and then sort it so that they sort nicely. I'm gonna call this labels. That's the unique labels in my data set, right? So how do I transform the original YS, the input strings? I'll just do labels.map. Right? Gonna print it nicely for each printing. Yep. So this is my one-hot encoded set of labels. So it's like 1, 2. So 1 is the first position. That's A and B, C, and B, C. Make sense? Yeah. So we notice the pattern: map into something summable, reduce. This is already pretty tedious on a single feature, right? And most of our algorithm takes like 400, 2,000. Like, let's try doing it on a column of two features, two input fields. All right, so it's a sequence of tuple 2 of double and string, right? Let's say I want to apply 3 transformations, the binarizer and the min-max on the first column, and then the one hot on the second column. How do I do that? It's doable. It's a lot of work. So the input tuple, let's say, first we have to compute the min, max, and the set. So let's do this. Underscore 1 min max set of underscore 2. All right, sum option. Miss one. Yep. Dot get map. So I have a tuple 3. The first one is min. Underscore 2 is. Okay. And the 3 is what? It's the set, right? So to sequence and then sorted. Oops. So you're getting used to this new Mac keyboard. Always blame the keyboard. Survived. Great. All right. Command line history to the rescue. Oh, I messed up my input as well. I'll just reset. No biggie. Go back. It's a lot of work. It's a lot of typing, and just for 3 columns. Try that for 200. That's not a fun thing to do. Go back here. All right. Hope I have history. Yes. X is. No. That's my sum option. Sure. All right. All right, almost there. So let's see. Sorted another parenthesis. This will give me x min, x max, and the labels. It's options. So I have to get. Anyway, it works. It's a lot of work, but it's doable. Now I can compute the summary of all 3 transformers. Actually, just the 2 the min, max, and one hot. But I can do both of them in a single run, and then I can do data.max map using the statistics I just computed. Say. So that's the first column. The second one will be min max. So it's underscore 1 minus x min. Same thing over again. So this is the min max scalar, and the third one, that will be my one hot encoder. So labels.map. Okay, and then that maps to the string column. Just add parentheses until it compiles. So it works, but even just for 3 transformers, it's hard. And I can't imagine doing for more than that. So let's go back to the slides. We noticed some pattern, right? Binarizer, the input is double, output is, the transformation is just a single map function from double to double. That's easy. Min-max input, min-max scalar, input is also double. First, we have to do a map into something that can be summed in parallel, in this case, a min and a max data structure. that has the proper behavior. Then we do a reduce. So reduce does the mean on the mean column, max on the max column. We map it again into the mean and max. That's the summary of the data set that we want. And then we remap the original data set with this summary. So simple, map, reduce, map to compute the summary of the data set, and then do another map over the original data set to compute the new transform data set. One hot encoder, similar, input a string. We map into a set that can be summed in parallel using a semigroup. Then after that, we map the set into sorted array or sequence. That's our labels, the global summary of our category. And then we remap the original strings into this, from a vertical data set into a horizontal vectors of ones and zeros. So we notice some pattern, and then we can abstract it in the following way. So with our input data, let's call it T. In this case, a tuple 2 of a double and a string. It can be anything like Avro or JSON, some kind of structured data. We extract some field, a leaf field from the record. Let's call it A. And then the MapReduce map pattern that we're doing is actually an aggregator in algebra, which basically means we map A into a type of B, which can be summed in parallel, and then we map B into C, which is the observed summary of our data set, or in this case, I call it settings. And then we transform the original A with C. So the A is the original input feature, and the C is the summary. That's where Featran comes in. It's also known as Featran77. Get it? No? F77, yeah, okay, get it. It's just a nerd joke. Anyway, let's go to the demo again before I explain the code. All right, so what we did before was a lot of work, and that's not easy to keep track of. That's not easy to maintain, especially if you're data scientist or machine learning engineer. You're like tweaking with feature engineering all the time, adding one, removing one, or changing parameters. It's hard. So let's do this instead. Let's import Featran and then import a bunch of transformers. Then we can do it in a more declarative way, say a feature spec, a specification of how to transform data for this input set of double and string. And then the first transformation we want to do is on the column _1, which is double field. And then we're gonna apply a binarizer. I just call it bin, okay. And then binarizer takes optional argument. Actually not optional, I think it's required. In this case, the threshold 42. That's the first feature we want to transform. The second one will be also the same, the first field, the double field, but instead we're gonna apply a min-max scalar. And I just call it min-max. Yep. And the third one will be the second field, which is a string. And in this case, we are gonna apply a one hot encoder. And I'm just gonna call it one hot. All right, and I'm gonna assign this to FS, a feature spec. Nothing has been computed yet. I'm just declaring the specification, but now I can use that to extract from my data set. I'm gonna call it a feature extractor. Nothing has been computed yet. It's just loading the data, and now we can do the computation. Feature names. I mean, certain feature transformations one-to-one, right? Like min-max and binarizer. It's input one column of double, output one column of double. The one hot encoder case, it's a little more complex. Input is one string, output is multiple dimensions. The number of dimensions is unknown until I've seen the entire data set, and which point I know there are 8 possible labels. This will give me that. So now I have the output dimensions or the columns. So 2, one for bit binarizer, one for min-max, and then 8 columns, one for each of the labels. I can do feature values to actually extract the values. And this is parametric, so we can specify what type of output we want. In this case, let's say a dense sequence of doubles, and then for each print and key. That gives me all the feature values in sequence of doubles, and it's already lined up, and it's pretty nice. We can also use a different output type. Let's say this is a dense representation. We can use a sparse one. It could be a sparse vector. It could be a map of string labels to the float values, or it can be something more complex, like a TensorFlow protobuf. This is like the typical way of feeding data into TensorFlow is using their protobuf data type, but it's also supported. Let's see. This is a string, the map of string to double. So this is sparse. All the zeros, all the missing labels in the category feature, the one hot, they are not present, and the ones, it's one label per input or per output record. So this is a sparse representation. Obviously, we can just do let's see, Featran or TensorFlow. Okay. Not Apache. Sorry, not everything is Apache. Okay. Example. All right. So I can just swap that output data type with example protobuf record. So that's what it looks like. All right. So far we talked about there's a feature specification. We can specify the columns we want to transform on and type of transformers, and then give us all the computation. It does one MapReduce map, the aggregator step. So basically translates to one MapReduce phase, and then the second map phase to transform the original data. So it's pretty efficient. We've seen that feature specification. And I just demonstrated the required fields. Fields can be optional. It can return an optional type, and then missing values can be treated differently. Feature extractor, we just saw that. We can extract name, value, and also settings. Actually, let's look at the settings. It gives me a string of JSON with all the parameters encoded. For example, the threshold, that's from the feature spec, but also from the data summary. For example, the min-max scalar, it observed that the min and max are 0.5 and 200. Why is this useful? Sometimes when I'm doing like machine learning, I'm doing feature extraction on a training set, and I can do like cost validation or evaluation. I could reapply the feature settings on a validation set without going through the summary again, because some of the transformation, for example, the encoders and the min-max, they depend on the summary setting. So that's useful. And other cases, it's useful. You can deploy it in a live backend or streaming service where you don't observe the entire data set ahead of time, because it's just infinite input of streams, and then we can transform each individual records, one at a time, using the previously trained settings. So for example, let's see. Our feature specification, let's say we can extract with settings, and then use that. Feature settings, get, no, it's head. All right. This case, let's call it's a streaming extractor. So it just loaded the previously observed settings, and I can extract feature values one at a time. Yeah. All right. So let's see. We want to extract a new pair of values. What about 100 and then A? It works. Actually, let's switch to a different. That's more readable. So okay, we can reapply the settings on a new pair of values. This case it works because both the double value and then the categorical value is within the boundary of the previously observed settings, right? What if I input X? It's not one of the 8 labels like A, B, C, D, E, A, B, C, D, E, F. Yeah. What happens? There's no one hot output because X doesn't fit, but instead we get, need to use a different method here, result. That will give me a unseen error of certain labels that's not being observed. So it's a feature rejection. We can reject certain data inputs, records, based on these kind of distribution. For example, if we remember correctly, the min and max was 0.5 and 200. So let's say try a -1. It got rejected as well because the range we observed previously was 0.5 to 200. -1 is out of bounds, so that doesn't work. And then it gives us the freedom to handle these kind of bad data properly. So that's feature extractor. And the nice thing is it only depends on 2 operations, actually 3 operations, MapReduce, and then the cross, which is basically map something with the side input. And it works in most data processing frameworks, Scala collection, Java collection, all of them have MapReduce operation. Spark, Scouting, Shield, Flink, all of them have the equivalent operation. So we can abstract that way. And it turns out this works on any of these frameworks. And the feature builder is what builds our output representation. So we've seen the map of string to double. We've seen the sequence of dense double. It can build vectors, sparse vectors, TensorFlow records, all of these. And again, it's decoupled from the actual computation, which is great. So it makes it a lot of flexible to plug in different data types. And again, feature builder, the implementation is super simple because we only need some abstract type that allows us to set a named value, like the feature name and a value, and allows us to skip some dimension if it's missing or in a sparse case. So that works pretty well. And we've seen settings. Settings allows us to save observation over data set to be used in a future transformation. So the first time I do it, with extract without the settings, it will do the MapReduce map and then the remap. Second time, if I load the settings, it will just skip the first MapReduce map and just use the straight one-to-one mapping. Other features that we've seen, rejection. You can combine features. You can have 2 specs and then merge them and operate on a single input. So that saves you the additional Hadoop job or the MapReduce map step. You can do feature crossing, like you can cross product features. In this case, it probably is the bad idea of crossing 100 million users over 100 million tracks, but it's possible. And you better use a sparse representation in this case, because a dense array of 100 million times 100 million is gonna blow up. And the last thing, because Spotify, we use Scala mostly for data processing, and then Java for production backend, so we can use the same library in both systems. So we will do the offline batch training, feed into TensorFlow, generate the graph and the settings, and in the live production backend, we'll load the settings and the TensorFlow graph and do live prediction. List of transformers, it's growing, it's easy to implement. As we've seen, you only need to implement like 3 methods, MapReduce map, to build your own transformer. Why did we build this? We look at other feature transformation libraries or solutions out there. For example, Spark has something built in. The problem is a lot of the existing solutions, they're tied to the ecosystem. For example, the Spark MLlib has feature transformation, but you can only use it with MLlib. We use TensorFlow and a bunch of other libraries, so it's more flexible if we can have something that's decoupled. And also, we don't really run Spark much. We mostly use the Google Cloud offerings, so it's nice to be able to run the same algorithm on any execution engine. And obviously, it's probably possible, but it will be hard to embed Spark in a production service. And your ops people will probably yell at you for doing that. Yeah. Anyway, and there's also Scikit-learn, which is a popular library for machine learning. this problem is it's in Python. There's no Java binding. That's one of the first issues. Second, scikit-learn works well on a local machine, single thread or single process processing. There's really no way to do that on a distributed system in a massive scale. So again, that makes it hard to use the same library for both training and for production serving. We like Featran because the execution is completely decoupled. So far, I've only demoed using Scala in-memory collection is an execution engine, but you can just run it on any of these four execution engines like Spark, Shield, Scouting, Flink. Again, it's a matter of implementing the three primitive operations. And the output format is, again, also decoupled. We can output in different formats based on the machine learning library that you're using, so it's flexible. The most common use case will be, in our case, will be output in TensorFlow records file, which is a binary format for TensorFlow, and then you can load it into TensorFlow directly out of the box. Some fun facts about this library: it uses property-based testing heavily with Scala check, which is a functional programming technique. Basically, instead of writing, handcrafting input and output data and making assertions of whether they should equal or not, property-based testing library looks at your data type, let's say a double, and it will generate all the possible, or a lot of possible combination of test cases, like edge cases like -1, +1, infinite, negative, infinite, and then you test on the behavior, you assert on the behavior of your library. It has 100% code coverage on the first try. Like I wrote the test, run 100%. Problem is, of course, that's what everybody says about testing. The absence of test failure doesn't necessarily mean the absence of bugs. So even 100% test coverage can have bugs. This is a super simple example of doing property-based testing. In this case, I'm writing a function that does normalization, taking a sequence of numbers, normalize them to sum to 1, like a probabilistic distribution. So I'm asserting on for any input sequence of double, the norm of the sequence should sum up back to 1, right? That makes sense. It doesn't work. For example, empty sequence, it's an edge case, yes, but it's not going to work on empty sequence. All right, so we add an extra condition, say, for any non-empty sequence, the norm of the sequence should sum up back to 1. Doesn't work. This is the test case that failed, which is a bunch of numbers, some of them pretty extremely large or small. And the nice thing about Scala check and a lot of the other property-based testing libraries, they have auto-shrinking, which means there's some heuristics to figure out the minimum case that will fail your test. In this case, just two numbers, one very large, and or actually, though both numbers are pretty small in this case, they will not pass the test. And there are some IEEE 64-bit floating number rounding errors, things like that we have to deal with. Bunch of other interesting cases where your algorithm may not work as expected, extreme cases. Some of them may matter, especially like normal anything statistical. Some of them, the extreme cases, may not matter as much, but it's up to the library also, like someone like me, to figure out what's the best approach to testing, what other cases I should cover versus cases where it's just too rare to even bother. But property-based testing is great, especially for any numerical statistical library, because it just allows me to focus on the business logic and not having to handcraft all these possible cases of input and outputs. Yeah, there are bugs. So some of the more interesting ones we've seen. The most common ones when you're dealing with any distributed system, closure serialization, it's a JVM thing that's just probably not fixable, but making things serializable or transient so that they survive the trip from your local master node to the Spark workers or something like that. It's usually like a majority of the data infra engineering effort is dealing with serialization. Concurrency and mutable state, another common problem, especially we do a lot of low-level optimization by sharing in-memory arrays and stuff. It usually is not a problem in a distributed system like MapReduce, because everything is single-threaded by nature and just make copies, immutable copies. This is more of a problem when you deploy the same algorithm in a concurrent multi-threaded backend service, and then they start to corrupt states, and then you end up with weird bugs. Performance, a lot of performance nodes took some time to improve the performance of the library, and did a lot of tweaking. Always micro benchmark. SBT-JMH is a good library for micro benchmarking. It's another Scala thing. While loops are usually better than full comprehension, so a lot of handcrafted while loops. Specialized primitive arrays, that's another Scala feature that numerical library designers use. Basically, instead of having lists, generic lists or sequences of Java box types, we can specialize them into just flat primitive arrays, and which improves performance hugely. And the right data structure. In a lot of the times we use approximate data structure like quantiles, things like that, and also benchmark the right approach. Use case. Actually, this is gonna be the first talk in the afternoon where Sammy, my coworker, is gonna talk in details about how we use that in production, but just a sneak peek. One of the service that we she works on is homepage ranking, so you have a lot of input features, number of items, the content that we want to present to users is recommendation. Some of context variables features like time of day, users attributes, stuff like that. We have to massage them into a numerical format that can be fed into TensorFlow. And then the architecture of the system, we have the same feature transformation library that's deployed both in batch pipelines and backend services. And we have a batch pipeline that computes the statistics, which is then loaded into a production service. And the same with the TensorFlow model graph, also both trained from a batch pipeline deployed in a production service. The three green components are where Featran deployed. Service code versus Scala data pipeline code. It's the same, almost exactly the same. That's it. That's all I have. And questions? Yes?
If I understand correctly, the actual engine is implemented on the JVM, but there is this JSON representation of the transformation graph.
Yes.
Is there any engine for over execution environment like native code or .NET virtual machines, and do you think it would be interesting or doable?
Okay, the question is, yes, the library itself is implemented in JVM if there will be the JSON in the settings if it will be useful in another language or platform. Yes, the answer is yes. We didn't implement all the other languages because JVM language, Java or Scala is the main language that we use. But most of the transformers, are pretty simple. And if you have the setting, all you need to implement to transform data is just the map function at the end. In most cases, it should be doable in any other language as long as you find the correct data type that matches. There might be some precision loss, or depending on how different languages treats float versus double or some kind of numerical values, there could be some precision loss. But in most cases, it should be easily doable. That's one of the reasons that we implemented this way, just in case if someone has to re-implement the transformation logic, say in Python, we can just look at the JSON and do that as a single map function.
One question is, you mentioned while loop has a bad performance in Scala.
Yeah.
Then just write, let's say, sometimes I write a sequence map, some range map.
Yeah.
Why that while loop has a...
It's there's a pretty well-known ticket. So the question is, why is while loop better than like the alternatives are either .map, for each, like the combinators, collection combinators, or for yield. There's a pretty well-known ticket. You can probably search like Scala while loop. It's the top result. But the short answer is most other alternatives gets translated into function calls. So every time you map one element, it gets translated to a function evocation, you know. And functions are actually not first class citizens in JVM. They are like just, until Java 8, they used to be just instance of a trait. So there's additional cost in doing that. Like nested for yield gets translated into like flat map, chained flat map, and a map. So those are additional costs. Yeah. But those are the things that data scientists or engineers normally don't worry about, because we do it in the library so that, you know, it does the heavy lifting, and the engineers can focus on defining business logic.
Do you use like TensorFlow queues and then just your data from the Spark side into it that way, or Scala side that way, or are you doing this like right into a file and then
We write into files in most cases. So we do it mostly, so we do the feature engineering in a batch job, which writes TensorFlow record files. It's actually like supported in Apache Beam. We added support, so you can write directly raw TensorFlow files, and then TensorFlow usually loads them on a single machine. Yeah, and TensorFlow, because we are on Google Cloud, so we write to GCS and Google Cloud Storage, and TensorFlow has built-in GCS support, so you can read directly from GCS. Anything else? Guess that's it. Lunchtime.